Alrighty guys, let's take a look at this problem here. It says, Eureka! You and a team of top scientists have discovered a new planet. Congratulations. Somehow all the other astronomers missed it. Wow, I can't believe that you guys found something that people have been searching their whole life for and still haven't found it. Your planet has a mass of 3.41 times 10 to the 26 kilograms and is 647 million kilometers away from the sun. The sun has a mass of 1.989 times 10 to the 30th kilometer. Oops, I meant kilograms, not kilometers. Kilometers are for distance, kilograms are for mass. What is the force of gravity between your planet and the sun? All right, so if we're trying to figure out force gravity, we're going to need an equation up here that has to deal with force gravity. Our force gravity equation is right here, so we're going to go ahead and use this one. So let's start with number one. There we go. Sorry about that. So let's start with number one. We have Fg is equal to big G times m1 times m2 all over r squared. So we know that m1 is the mass of our planet or the sun. It doesn't really matter. So the mass of our planet is right here. So we're going to take the mass of our planet. I'll just write it down over here so that we have it. So we have m1 is equal to 3.41 e to the 26. E and times 10 to the 26 are the same thing. So e to the 26. And then we have m2, which is going to be the mass of our sun in this case, is 1. It's an ugly looking 1, but it'll do. 1.989 e to the 30th. All right. And then lastly, we just need r. R is the distance between the two planets, and it tells us that the distance between the two planets is 647,900,000 kilometers. We need to make sure, though, that we're converting this to meters, because when we talk about distance, it needs to be in meters. So I'm going to go ahead and rewrite that number, 647,900,000. And then in order to get this into meters, I'm just going to add 3 zeros to it. So now I have a giant number here and 2 more giant numbers there. I'm going to erase this 1 and make it look more like a 1 real quick because it kind of looks a little ugly. All right, so after that, all we have to do is just plug our numbers in. We know that big G is our universal constant, which is always just 6.67 e to the negative 11th. So taking these numbers and plugging them into our equation, we find out that force gravity should be equal to 1.078 e to the 23rd. And since it's a force, that's going to be newtons. All right, number one's done. Let's take a look at number two. Number two says, what is your planet's centripetal acceleration? So if we're talking about centripetal acceleration here, we're going to need our centripetal acceleration equation. We can see that we have two equations with acceleration in it. We have AC equals v squared over r. In order to use this one, though, we need the velocity, which we don't have. And then we also have A equals our net force divided by m. So since we don't have our v, we can't use this equation. We're going to have to use this one up here, where A is equal to our net force over m. So A equals F net, meaning net force, divided by m. So let's take a second and think about this. Which object is experiencing this acceleration here? Is it the planet or is it the sun? Well, it's asking for our planet's centripetal acceleration. So because of that, we're going to need the mass of our planet. So we're going to go ahead and use m1 again in this case. The force, or our net force, well, what net force is acting on this object? If we were to quickly draw a picture of our planet, so here's our planet and here's the sun, we know that this planet is going to rotate and orbit around the sun. What is pulling them towards it? And when we're talking about our net force, we're talking about our net centripetal force. So what force is pulling them inward? Well, the only force that's acting between these two planets is going to be force gravity. So our net force in this case is force gravity. So let's go ahead and plug these numbers in. We have our centripetal acceleration should be equal to our force gravity, 1.078 e to the 23rd, divided by the mass of our planet, which is 3.41 e to the 26. Okay? It's important that when you guys plug this in your calculator, you put the bottom in parentheses and you put the top in parentheses. Make sure we get the right number. We do the math. We find out that our centripetal acceleration, going to add a little c here so we know it's centripetal acceleration, is going to be equal to 3.16 e to the negative fourth. Since it's acceleration, it should be meters per second squared. Alrighty, let's take a look at number 3. So number 3 says, what is the velocity of your planet? So again, we're just going to look at our equations up here and look for an equation with velocity. We have 2 of those. We have one right here and one right here. In order to use d equals v times t, we would need to know what t is. We don't have t, so we can't use this one because we're also solving for v. Therefore, we're going to have to use this equation over here because we know what AC is. We just solve for it, and we know what R is because it was given to us in the problem. So let's go ahead and solve for this. I'm going to go ahead and rewrite my equation, which is AC is equal to V squared over R. It's asking me to solve for V, so I'm just going to rearrange it for V. It means I'm going to multiply my R over. So I get R times my centripetal acceleration is equal to V squared. I have to square root both sides to solve for V. That means that V is going to be equal to the square root of R times centripetal acceleration. Perfect. We have the centripetal acceleration from before. It's just 3.16 e to the negative fourth. So again, this is our centripetal acceleration. And then R is the same thing it was before, which was just 647,900,000 kilometers, but I turned it into meters, so that would be billion. So I'll rewrite R again just to make sure that we're using the right value. 647,900,000,000 meters. Okay? All we do is take those, plug it in, and we end up with a velocity of 1.43 e to the fourth. So 1.43 e4. And since it's velocity, it's going to be meters per second. Alrighty, there we go. We got 3. Let's take a look at number 4. So number 4 says, how long is 1 year of your planet? So now it's talking about time. So if we want to figure out what time is, we're going to need an equation with time. Fortunately, we only have one equation with time. It's right here. So we're going to have to end up using this equation. But we need to solve for d. We don't know what d is. The question is, how long does it take for one orbit? One orbit is going to be this entire distance here. And this distance is also known as a circumference. So d is actually going to be equal to circumference, which is 2 pi r. So let's go ahead and rewrite all this stuff below, where we have d is equal to v times t. And we also know that d is equal to circumference, which is equal to 2 pi r. So let's take what we know, because we don't technically have a d and we don't technically have a c, but we do have an r and we do know pi and we do know 2. So we're going to take this and plug it in over here for d. So we get 2 pi r is equal to v times t. Again, we're solving for t here, so we're just going to manipulate this to solve for t. So I'm going to divide by v. So that gives me t is equal to 2 pi r divided by v. Now, all I have to do is plug my numbers in. My r is the same that it was before, which is right here. So I'm going to reuse this r. And then my v, I just solved for. It was right here. I'm going to use this v. So plug these two things in. When I plug it in, I'm going to get my answer, which is going to tell me that it is 7.9. Oops, that's the next one. My bad. My answer should be 2.84 E8. And we need to ask ourselves, what are we solving in? What are the units here? Well, our velocity is meters per second, and our radius is in meters. So meters divided by meters, those are going to cancel out, which means that our time is going to be in seconds. So this is how many seconds it's going to take to orbit. Now we want to figure out how many hours. Well, we know that there are 3,600 seconds in 1 hour. So we can just take this number and divide by 3,600, and we end up with 7.9 E4 hours. Okay. Now that we have hours, we're almost there. We want to get days. Well, we know that there are 24 hours in 1 day. So we're going to take this number and divide it by 24. And that's going to tell us that it takes 3.29 E3 days. And then lastly, almost there, last part, we want to figure out how many years. Well, we know that there are 365 days in 1 year. So we're going to take this and divide by 365. Doing so, we're going to end up with 9.02 years. And all of this is relative to the Earth. So that's how many Earth years, Earth days, Earth seconds, Earth minutes, and Earth hours it's going to take.